Principal component analysis is normally a dimension reduction method which normally compute what we call principal components, and these principal components are used subsequently in trying to understand what is going on in the data. So the main thing that you need to remember with principal component analysis is that it is a dimension reduction method. When I refer to as a dimension reduction method, what do I mean by that? Let me just give you an idea. Let's suppose you have a data set, like an insurance data set, where you have different individuals in the data. And you have different information pertaining to these different individuals, like their age, like their gender, and so on and so on and so on. Like, let's suppose there are many variables, many information about these different individuals, like x1, x2. All these are the different information. Like you have p. Let's suppose p is 100. Like you have 100 variables related to the to each policyholder. All right. So you have several variables related to these policyholders. Now, trying to analyze this data with 100 variables is not something very easy, or is not something that is always good to do. Why? Because you will note that sometimes many of these different variables in the data set, they are correlated among themselves. We already discussed correlation. They are correlated among themselves. And if they are correlated among themselves, then it means that one kind of explains a little bit the other. So if there is a sort of high correlation between them, you might allow yourself to remove some of these variables and get a smaller data set which you where you have less correlation, right? Where they are uncorrelated basically. You might want to come up with a smaller data set. Instead of having 100 variables, you might come up with 7 variables which are uncorrelated among themselves, and you analyze these 7 variables instead of analyzing these 100 variables which are correlated among themselves. That's the idea behind applying principal component analysis. We are going to reduce the dimension of a data. Like if you add 100 variables, in the end, you will come up with 7 principal components. All right, 7 principal components. That's what we refer to as components. Basically, what you are going to do is that these different variables, like x1, x2, up to x100, will come up to a new variables, a set of variables. A new set of variables which are now uncorrelated. Let's call them Z. All right. So they will come up to a new set of uncorrelated variables. Like there are correlation between x1 and x3, maybe x1 and x10, there are correlation between these. But then later on you come up with a new set of variables which are uncorrelated normally. So that is the idea behind principal component analysis. So you move from 100 to a fewer set of variables, and these fewer set of variables, they are uncorrelated, which means that now they explain a lot of information with regards to many of these variables. So instead of having 100 variables, you get less with still a lot of information with regards to these 100 variables. So this is what we are going to do. We want to come up with a smaller set of variables. And to do that, we apply what we call the principal component analysis. So as I said to you, we are doing a right dimension reduction method, and what we are getting is that we are getting principal components which are uncorrelated set of components which can be used for regression to avoid issues of multicollinearity. Multicollinearity means you have correlation between different variables x1, x2, x3, and so on, up to, let's suppose, x10. You have correlation among these different variables. I suppose you might have correlation between x1 and x3, a very high correlation of, let's suppose, 0.9 between x1 and x3. Then it's not necessary for us to use both of these variables. We could use only one, or we could use a transform version, which we are going to discuss in the principal component analysis. Now, uh, the transform, so basically, as you would note here, is that we are moving from x to a new set of variables, z. So if you have understood well, you are going to apply a certain kind of transformation, and this transformation will reduce your data set according to what we are seeing. Now, so your Z will be transformed into a new set X, your X will be transformed into a new set Z, excuse me, and this goes on like that. And then you're not going to use all of the different possible Z that you might have, but you will use only a few of these Z, which explain most of the variation in the data. So you will see that normally when you're applying the transformation, you don't get 7z, you will get still p possible values of z, but in the end, you will be using only a few of them, which explain most of the variation in the data. That's why you saw me saying that we are referring to 7, for example, instead of all the possible values of uh, x that you have, that is p, which was 100. So you will still have z 100 values of z when you apply the transformation, but all of them are not necessary because they do not explain much variation, and only for example, I say 7 might explain most variation, so I retain these 7. Or it might happen that 5 explain most variation, so I retain those first 5 principal components. That's the idea behind. I just made a quick overview of what is supposed to be about, what principal component is supposed to be. So, as you understood, principal component is mathematically refers to a sort of transformation, all right? A transformation that you need to apply to your data. Now, what you need to understand is that normally what PCA is about is that it is mathematical. It normally it refers to a rotation of your data. I'll just explain this to you, and then I'll just mention this to you, and then I'll explain it to you more clearly. It normally applies a certain rotation to your data for one purpose. The purpose is to capture variation between these different variables. You might ask yourself, what am I referring to? But I'm going to get into that in a moment through an example. Let me just mention it first. We want to come up with components that are not correlated together, as we said earlier. So we want to have, when we say that, we want basically to have the highest spread between these components. When we say that we want to have components that are not correlated together, it means that we want them to have the highest spread. Try to understand the concept of covariance. Covariance, if they are uncorrelated, the covariance will be close to the variation between these data. Like, remember that if you have two variables and if you have a data that is like that, if the data is like this, it means that there is very low variation between, there is very low correlation between them. And if there is low correlation, it means that the variation between these different data is very high. So, however, if you have a data that is like this, the variation is relatively small and the correlation is going to be high. So that's what I mean by the fact that we want the highest spread between these components. When we say we want the highest spread between these components, we are basically saying that we want components that are not correlated among each other. And for this, we will need to make use of something that we call basically the eigenvector and something else that we call the eigenvalues. This is just for your information. I'm just giving you an overall idea of what we will require. We will need something that we call an eigenvector, which will give us the direction of these different components. All right. What do I mean by that? Let me come back to that afterward. And eigenvectors of the covariance matrix are usually the directions of the axes where there is most variance, right? The eigenvectors basically is the eigenvectors rather is a concept that you use related to the covariance matrix. It's something that you get from the covariance matrix, which is basically giving you the direction of the axis where there is most variance. And we call these what we call principal components. So just a quick recap, I said that we will need to find something that we call an eigenvector. All right. This eigenvector is basically what we call the principal components. All right. And it is the direction of a line that gives you the maximum variance between the different points. That's the idea behind what we call the eigenvectors. But before I get into the details of what we call eigenvectors, let me explain to you what I refer to by maximum variance, or the highest spread between a set of points. And I'll give you a small example here. I'll give you a small example. Suppose you have only two variables in your data set, right? You have only two variables, x1 and x2, and you want to find what we call principal components. Now, here, of course, there is no reduction to do in the data, but you can still find the principal components. There's no need for reduction of data, maybe because you have only two variables. So principal components is basically applied for many variables, obviously. But to explain the concept, let me just take only two variables. So what is going to happen? Let's suppose you have four different points like this. Okay, four different points like that. And what I want to do is, I said that we need to get what we call principal components. And what basically the principal component do? The principal component is going to give you a sort of line that goes through that data in such a way that this line explains the maximum variance. Let's suppose I take, so we are applying a rotation of the data, but I will talk about the rotation in a moment, not now. Let's suppose I take a certain kind of line that goes in the data like this, all right? A certain kind of line that goes in the data. And if you look at the perpendicular distance between the point and the line, the perpendicular distance between the point and the line, this is what I refer to as a perpendicular 45-degree line, 45 degree between the line and the point. So I look at the perpendicular distance between the point and the line. That's basically what I get. And let's suppose I imagine that these points are on an horizontal line. Let's imagine I rotate that line, okay? I rotate that line, I make it become horizontal like this. An angle of 180 degrees. And let's try to locate these different points on the line here. Let's try to reproduce these different points on the line here. You will see that this point here, this point, I'm not going to write it down, but this point here, let's suppose it is here. And let's suppose this point on the line here is somewhere here. And then there is a relatively big distance between the next one, let's suppose here. And then you've got something else a little bit same like this one. This is what we get. So we have a sort of spread between these different points. You have an average, which is in the center somewhere here, all right? The measure of central tendency, the average is somewhere here, and you have a spread between these different points, and of course, which is measured by an average, let's suppose, the spread between these different points. But let's now take another example of a different line, So just remember what this is about. I'm going to erase this line now. I'm going to erase this line, or let's keep it just for you to get the proper reference. So let's take a different color of a line. Let's take this black line now, which goes in the center. Okay, get something like this, which goes in the center. And then we are going to evaluate the distance between the perpendicular distance between the points and this black line. So the perpendicular distance, if you look at it properly, you will see that it is around here. Okay, sorry for this small mess here, but I guess you will see that this is here. And then this one is what? The perpendicular distance is around here again. This one is here. This one is here, or very close to it. Sorry for this small mess, but this one is very close to it. Excuse me. Uh, the perpendicular distance, as you see here, for these same point that you add here, are like this. Now we are going to reproduce this black line. We rotate it on 100 degree now, right? We rotate it on 100 degree, 180 degree, excuse me, line like this. And then we try to locate these different points on that line. So we will see that we will get something a little bit similar to that. You see that the points are relatively closer here for these first 2 points. And then what you get is you move further away, very far away, and then you get again these 2 points that are very close to each other. Now look at the red line, how it was, and look at the black line, how it was. If you were to reproduce these points on a rotated axis like this is what you will get. And again, of course, you can compute the mean for these different points, all right? The average for these different points. Now let's try to figure out, according to you, if I ask you the question between A and between B, which one has got the maximum spread? Is it B or is it A? I think you would all agree with me that it is A which has got the maximum spread. So as you see here, we are trying to figure out what line will basically give me the maximum spread, the further, the highest variance. This is the one, A is the one with the highest variance compared to B. B has got a variation, but it is smaller than that of A. A has got a higher variation than B. So in other words, what are we trying to do here is that we want to find what we call a principal component. A principal component is like basically a line that goes in the data in such a way that through this line you get the highest variance. The highest variance means the further distance away from the mean, obviously. And this is like in this example, if you were to look at between the red line and the black line, you will see that it is the black line which gives the highest variance. And if this was the only two possible lines that existed, then the black line would have been the first principal component. This is what the principal component would be, the one which gives you the highest variance. But of course, how do we determine that line then? That is the question that we need to ask ourselves. How do we get that line? And that line comes through the principle of what we call eigenvector. If you want to find that line, you need to find the eigenvector. Eigenvector means you have the direction of a line that explains the maximum variation between these different points. There is a certain direction of a line that gives you the maximum variation between these different points. And this is the eigenvector. Vector refers to the direction of a line, and you want that vector, and we call it the eigenvector. We want that vector that gives us the maximum variation. For example, this red one does not give you the maximum variation. This direction of a line does not give you the maximum variation. But the black one gives you the maximum variation. So the black one could have been considered as the eigenvector in this context. So this is what I was referring to when I talked about principal component analysis earlier. I was talking about the eigenvector, which you need to find, which refers to the direction of the axis. And as I also said to you earlier, what we are doing here is that we are referring to a rotation of your data to capture easily variation between your variables. You remember that I said earlier that you want principal component analysis mathematically is applying a rotation to your data in view of capturing easily variation between your variables. Like here, you add your data like that, and what I'm doing is that I'm rotating it in this way. The same data like here, I'm rotating the line in such a way that I can capture the maximum variation. So what is going to happen then when you're applying principal component analysis? You are basically getting a new data, a new transform data. A transform data where now you don't have x1 and x2, but you have z1 and z2 in such a way that these transform data will be rotated on a new axis. Instead of having this like that, you will have a new set of values like this, for example, and this point will be transformed from a place to another one. They will be rotated, all right? And when they will be rotated, it will capture the maximum variance. You are finding the line that will capture the maximum variance. If you used this line to rotate your data, you would not have had your points in a way that you get the maximum variance. But if you use the black one, you will get a new set of uncorrelated variables where your points, of course, are more spread than another one, like the red one. So that is what we are doing. We are transforming the x1 into a new set, z1 and z2. And then, obviously, what is happening is that you will have the these two variables are uncorrelated. Like here, x1 and x2, you see that they are correlated. But z1 and z2 will be uncorrelated because the points will lie like this and will lie something like that. And if you look at that, there will be no variation between, not variation, but there will be no correlation when you have a data that goes like this. All right, as I explained to you in the context of correlation, you remember if you have a data, for example, like this, it means that they are uncorrelated. So in the same way, that's what we want to do. We want to apply this transformation to make them become uncorrelated. If they stays like that, the data, they are correlated. But if they become like this, they become uncorrelated. That's a little bit what we want to do with principal component analysis. So we want to come up with a new set of principal components which transform the x1 into a new z1, transform the x2 into a new z2, but I'm not going to get into the transformation details here. I'll leave that for the new module that you're going to learn with me next year. All right. But what I want to do today is to explain to you how to get this eigenvector. This is the most important part what I want to do today. I want to explain to you the concept of what we call eigenvector. In other words, I want to explain to you how you get the direction of the line that explain the maximum variance. And of course, you're going to apply the rotation to it. So this is our next step. We need to explain what we call eigenvalues and eigenvector. Of course, to understand the concept of eigenvector, you need to understand what an eigenvalue is first. We are going to discuss that, and then you will understand what eigenvectors represent. To find the principal components, you will need to be able to find the eigenvector of the variance covariance matrix, which we are going to get into later on. But the first thing that we need to do is to understand what an eigenvector is. So we will just take a small example to illustrate that, okay? We'll explain first of all what an eigenvector is, but to be able to understand the eigenvector, we need to find the eigenvalues. What are eigenvalues? The eigenvalues of a matrix A are the values that we refer to as lambda, such that the determinant of the matrix A minus lambda times the identity matrix equal to 0. Now, the eigenvalues are specific values lambda which satisfy that equation here. So our first step is to know what is our matrix A, all right? And then we will need to know also what is the identity matrix, which we all know what it means. And then we will need to find the lambda from that equation by setting the determinant to 0. So let's have a look at an example to illustrate that. And then, but before we get into that example, when you've got your eigenvalues, then for each eigenvalue, you will have an eigenvector. If you have two eigenvalues, you will have two eigenvectors. Three eigenvalues, three eigenvectors. Like in the example of a 2 by 2 matrix, you will have two eigenvalues. And if you have two eigenvalues, you will have two eigenvectors. So let us try to find, first of all, our eigenvalues. So I repeat, the corresponding eigenvector of an eigenvalue satisfies now an equation which is A minus lambda I times the eigenvector equal to 0. Normally, the eigenvector will always satisfy this equation that you are seeing right there. But before we get into all this, let's find the eigenvalues. So as we just said here, we need to find the determinant of A minus lambda I. So what is A minus lambda I? A minus lambda I means you need to take the matrix that you've got, 7, 3, 3 minus 1, and then you need to subtract lambda into 1, 0, 0, 1, which is our identity matrix. Obviously, here I'm assuming that you already have a notion of matrix manipulation in other courses, so we are going to use these notions to be able to understand what to do here. So you have 7 minus lambda, 3 minus lambda times 0, which is 3, and then you have 3 minus lambda times 0, which is 3, excuse me, and then you have minus 1 minus lambda times 1. So in other words, it becomes minus 1 minus lambda. So that is A minus lambda I. This is our matrix A minus lambda I. So what is our next step? Our next step is to find the determinant. The determinant is obtained by taking 7 minus lambda multiplied by negative 1 minus negative lambda, subtract what you've got here, 3 times 3. And then you set it to 0, and this is what is going to give you your lambda value. So let's show what I did here. So this is already explained. What we need to do is to find the determinant, which is also represented by these two bars here. So we take this 2 multiplied 7 minus lambda multiplied by negative 1 times negative 1 minus lambda minus 3 times 3 here as we did, and this is what we get, lambda squared minus 6 lambda minus 16. And what is the next step? We need to say this is our determinant. We need to set it to 0 in view of finding this lambda. So we set it to 0, and obviously because it is a quadratic equation, you will note that there are two possible answers for that, and it is lambda equal to 8 and minus 2 that are the possible answers that you get from this determinant. So you have noted that there are two eigenvalues, and for each of these eigenvalues, you will have eigenvectors associated to them. We need to find eigenvectors now. To find the eigenvectors, let us just recall what we just did earlier. Here we go. It states that to obtain the eigenvector, what we need to do is to solve this equation. So we've got our values of lambda. There are two possible values of lambda. So you will have two eigenvectors corresponding to these two possible values. So we'll start by the first value, lambda. Let's try to see what we got. We got 8 and negative 2. So we'll start maybe by lambda is equal to 8 and replace in there. And then when you've replaced it in there, you will set it to 0. For example, you have a minus lambda I, which is already written here, a minus lambda I, which we got already here. So what we just need to do is to say a minus lambda I for lambda equal to 8, a minus lambda I equal to what? 7 minus 8. I'm just going to write it down like it is so that you don't get lost in what I'm doing. 3 stays 3, 3 stays 3, and then here you've got minus 1, minus 8. This is what you have as the matrix for lambda is equal to 8. So you have minus 1, 3. So we have the first matrix that we have. And then we will say that this matrix will have to be multiplied by a certain vector that and then the multiplication will result in a value of 0. So, in other words, what we are just saying here is that this matrix -1, 3, 3, -9 that you got here should be multiplied by a certain vector. Obviously, there are going to be two possible values for that vector. We're going to call it nu1 and nu2, all right? And then we will say that this is equal to 0. And we just need to solve for to find v1 and v2. That's what we did here. So we have -3, that's already explained here, right? I've already explained that. And then you are going to multiply negative v matrix A minus lambda I for lambda equal to 8, and you set it to 0. That's what I do here. And then we just need to find the v1 and v2. Now, to be able to solve for v1 and v2, you can apply the row reduction method. And the row reduction method means what? You want to solve the matrix by finding nu1 and nu2. So by applying the row reduction method, you have -1, 3, 3 and -9, and you have a solution to the equation which is 0 and 0. Then you need to apply this row reduction, which you have already probably learnt in other courses with regards to matrix manipulation. When we say that we want to row reduce a matrix, we just a quick reminder rather, or a quick recap rather of something that maybe you have done or not, but let me just tell you, is that normally you want the first number in the row to be a non-zero element, all right? We call that the leading coefficient. The other thing is that we want the leading coefficient to be to the right of the one above it. We want the leading coefficient to be to the right of the one above it. For example, if you have 1, 0, 2, then you want the next leading coefficient, 1, to be just one right above it, and this one should be 0. All right, and then whatever this one could be, but the idea is that if you have 1 here, the next one should be the one should be on the right of this one. And then the other thing is that you have any non-zero element which are always above rows with all zeros. Any non-zero element which are always above rows uh, with all being zeros. For example, you have let's suppose 2, 0, 3, for example, and then you have, for example, here 0, 0, 0, things like this. All right, this is also a row reduced row echelon. This is in the row echelon form. All right, so we want something a little bit like this, where you will have where basically you want to solve the equation in an easy way. So this is just a matter of mathematics that you have probably been doing, I guess. So, but I'll just mention it to you in case you don't know. So what do we want to do then is to row reduce this matrix. To row reduce this matrix, basically we want to bring all these elements down there to 0. This could be a non-zero, it doesn't matter, but at least this one should be a 0, as the first one should be a 0. All right. How do we do that? We need to apply certain manipulation to this equation. For example, we want to bring that row, or more particularly this one, to 0. If we want to bring this first row to 0, the first number in the second row to 0, what we want to do is we want to apply a certain equation that we are not changing anything. We are just applying some transformation to the numbers. Like the second row, as you see here in this equation, the second row is equal to the first row multiplied by 3, and then plus the second row. So if we want to manipulate that row here down there, the first one stays as it is because we want to change the second row. So the first row doesn't change, it stays as it is. And the moment that we got a 0 here and everything is 0, if everything as well is 0 down there, it means that you have already row reduced the matrix completely and you don't need to worry to go to another step further. Let's try to see if what we get when we apply this formula that I've written here. We want to make this become 0. The only way to make this become 0, as you would note, is by taking the way that you can use the means by which you can make this become 0 is by taking the first row -1, and then what you need to do is to multiply it by 3, which gives you 3. But then what you have to do, sorry, which gives you -3. Then what you have to do is that you won't get 0 from that, but what you need to do is to add this number that you got with the second row elements. So in other words, by adding the second row element, which is 3 here. So if you add 3 to -3, you get 0. This is how I've been able to make this number become 0. I repeat, how do I make this number become 0? Is by taking the first row. I'm talking about the first element of the first row for the time being, but this applies to all the elements of each row. To obtain the new second row, what you need to do is to take the first row, which is -1, multiplied by 3, and then you need to add 3 to it. All right. So, but how do I get to add 3? It's only by this number that you got here. Why did I choose 3 here? Obviously, you would have understood that I chose 3 because I know that the row below it is 3. And if I multiply by -1, I get -3. And if I add with the second row, I will get 3. If I decided to choose another number instead of 3, I chose 4. I would never be able to get 0 here. It would have been very complicated to get 0. So the best way and easiest way to do so is to take the first row multiplied by 3, which is -3, plus what you got here. This is how I got the first term here, the first coefficient here to be 0. Then what do? I need to apply the same principle to all the elements that you got here. The principle said we need to take 3 times the first row plus the second row. 3 times 3, which is 9, plus what you got in there, which is -9. So 9 plus -9 becomes 0 again. Now, the next step is to take this, what you got here, 3 times 0, which is 0, plus 0, which is again 0. So that is why we chose to use this equation here. We chose to use this equation because in the end you've got a row-reduced matrix where you can solve it easily. All right, you got a row-reduced matrix. I repeat, the choice of what you got here as 3 obviously depends on the first row where you want to eliminate it and make it become 0. If it was a 4 here, if this was a 4, then you would not have multiplied by 3, but multiplied by 4. All right, to make things easier for you. So we got that row reduced matrix, and from that row reduced matrix, then life becomes simple, right? We've already done the row reduction. So you would say that now you can say that -1 times um, -1 times v1, because remember that originally this is what you got, and you have -1 3 -1 v1 new one you choose is equal to 0 0. What you did is that you brought the solution of the equation in there, and then what is the solution to the problem then is that you have a -1 times v1, which you are not seeing here, plus 3 times v2. This is equal to 0. So this is what you get in this equation here, because of course the next one is 0. The next one is 0 times v1 plus v2 times 0 equal to 0. You don't have to solve this, but you have to solve only the first one. So you understand why I've reduced this matrix to make life far more simple for solving this matrix, all right? Now, we understand that 3 nu2 equal to nu1, all right? 3 nu2 equal to nu1. So by the way, we call that nu. It's a Greek letter that is called nu, all right? If you hear me say nu each time and you don't understand what I'm saying. So 3 nu2 is equal to nu1, and you've got an equation which makes it easy to solve. So what is the value of, what is the eigenvector that you are referring to here? The eigenvector, if we say let nu2 be equal to 1, if nu2 equal to 1, what is nu1? Nu1 is obviously equal to 3. If this is equal to 1, then nu1 equal to 3. So what is happening here? You've got your first eigenvector, which is 3, 1. Remember that nu1 comes first, and then nu2 down there. So maybe you would ask yourself, but what about if I say it is 2 here? If I say let nu2 be equal to 2, then what about nu1? Nu1 is equal to 6. This is also another eigenvector. So you have 6, 2. That's also another eigenvector. And you will see that these two, this one is a multiple of this one where you are multiplying by 2. So you will understand that you can have an infinite possible number of eigenvectors that are possible. But of course, they all have the same direction. The magnitude doesn't matter much, but it's the direction that matters. 6, 2, 3, 1 is the same direction. So remember that we are interested in the direction. The length is not really of importance here. The magnitude doesn't matter. All right. So this is a little bit what I have done here. So we've got our first eigenvector, which is 3, 1. Now, as I said to you, for this applies for lambda is equal to 1, and you have an infinite number of possible eigenvectors, which are multiples of each other. If you multiply by 2, that's another possible eigenvector, and it goes on like that, just for information. But here we are using one, which is, we just decided to put a new one, nu2 to be equal to 1, all right? But you could have decided nu2 is equal to 2. That's also a possible eigenvector. It's okay, it's fine. Now, this is the first one that you got, all right? This is the first eigenvector that you got, but what do you have to do? You need to find the second eigenvector now, which is for lambda is equal to -2. You remember you earlier that you got two eigenvalues. You've got the first eigenvector for the first eigenvalue. You have to repeat the same procedure that we got here for the next eigenvalue, which was -2. And you will see that this time I got an eigenvector of 1, -3. All right. By the way, you will see that you can check your solution if what you've done is correct by this equation. Normally, you need to check if when you take your original matrix A, all right, multiply by your eigenvector, do you get lambda times the eigenvector? All right, this is what is important to understand here. You are applying a scaling, a rescaling of your data. This lambda can vary, all right? So if you take A times your eigenvector, do you get a lambda times the eigenvector? And this is what I do here. I'll check if by taking the original matrix A, which was 7, 3, 7, 3, 3 minus 1, I multiply by the eigenvector that I just obtained for lambda is equal to 8, all right? That is 3, 1. And I see what does it give me. If by this I get a certain multiple of the original eigenvector, then this multiple is equal to, in fact, lambda is equal to 8, then I know that I've done something that is correct. So we can check it out and see what it gives. So if you take 7 times 3 plus 3 times 1, 7 times 3 plus 3 times 1, this gives you the first row. So you will have 7 times 3, 21, plus 3 times 1, 24. You can write it down. And then you have 3 times 3 plus negative 1 times 1. So it is 9 minus 1, which is 8. So you see that you got an eigenvector, not an eigenvector. You get, by taking 8 times the eigenvector, you get 24 times 8. Now, can you rewrite that as a multiple of the original eigenvector that I multiplied? In fact, you will see that 24 is basically 8 times 3 and 1. So 8 times 3 is 24, 8 times 1 is 8. So you have noted that indeed you have done what you have done is correct, all right? You've seen that A times the eigenvector is equal to a scalar times the eigenvector itself. So here the lambda is equal to 8 is the same as we used. And we can do the same thing for negative 2 and just check the same thing here. You will see that you will get again the same solution. You will see that everything is the same by taking a new, what you are going to get from lambda is equal to 2. You will see that it is going to be equal to negative 2 times your eigenvector that you're going to get from negative 2. You can check that later on, and you will see that the eigenvector is 1, negative 3. So maybe what I will do is, let me just do it for you so that you understand it better, all right? Let me just find out this for you. Lambda is negative 2. I want to show you that the eigenvector is 1, negative 3. Now, for lambda equal to negative 2, remember that what you have to do is the following. You have to find, you have to show that a minus lambda I times the eigenvector equal to 0. That's what you have to do. And lambda is negative 2. So what you want to do is that you want a minus lambda I for lambda equal to negative 2. You need to find it out first. So it becomes 7 minus lambda, which is, remember, 7 minus lambda. 7 minus lambda, and lambda is minus 2. So write it down like this. 3 stays as it is. Negative 1 minus negative 1 minus 2. So what is it equal to? It's equal to 9, 3, 3, and negative 1. So excuse me here, I've got this, yes, negative 1 minus 2. So negative 1 plus 2, which is equal to 1. So what we want to do is to take this, multiply by the eigenvector nu1, nu2, and equal to 0. So let's do it on the other side. 9, 3, 3, 1. Just remember that. Multiplied by the eigenvector nu1, nu2, and this is equal to 0. And again, to be able to solve that, as you already know, we are going to apply the row reduction method, where we are going to make this leading term become 0, and then things will be easier for us. So how shall we do that? So we'll just write this down in the form that is required. This is our form that we want, that is required. Now what we want to do is to row reduce this matrix. What is going to be R2 in such a way that this becomes 0? We can think about it for a moment. You will need to use R1 here, and if you think about it well, the only way to get this become 0, R2 is obtained by taking the first row, which is 9. Let's talk about only the first one. So it is 9 minus what? What do you have to do to get this to become 0? So the new row 2, that is this 3, will turn out to be 0. It's obtained by taking the 9, and you need to manipulate that as well, this 3. So it's obtained by taking 9 minus 3 times the second row. If you try to understand what I did, is the second row equal to the first row, which is 9, minus 3 times the second row. What is the second row? It is 3. So 3 times 3 is 9. So our 1, which is 9, minus 9 becomes 0. That's the way that I've been able to row reduce this matrix. So the first row stays the same as you have understood. But this one, when you apply this rule here, which says that the second row is obtained by taking the first row. What is the first row? 9 minus 3 times our 2. That is minus 3 times what you got in the second row. Minus 3 times 3, which is 9. So in other words, 9 minus 9 equal to 0. So we apply the same principle, of course, everywhere. We don't do it only for the first one. But bear in mind, it is that the first one that you look at to be able to apply this formula, because it's the first one that you want to make become 0, obviously. And then what you need to do is to check for this one. So it is 3, the first row, 3, minus 3 times the second row, which is 1. So it is 3 minus 3 times 1, which is again 0 in this particular context, and this is equal to 0. Now you have to understand that it's not always the same in all the different cases, all right? In many different cases, you might not get the same thing like I'm doing here, all right? Because this is a relatively simple case, but in other cases, you might have other different solutions, all right? You don't necessarily have zeros everywhere in the uh, second row. You might have 0 here, you might have a 1 here, it depends, all right? But for that particular context, you are having 0 everywhere. So it's okay, it's not a problem, as long as this one is a 0 here. Now, the next thing is to solve that again. So you know that there is a V1 and a V2 here. So you have 9 times V1 plus 3 times V2 equal to 0. So 9 times I'm calling it V1, but in fact it is new 1, plus 3 times new 2 equal to 0. That's what we got here. All right. So if you wish, you can also rewrite it differently. You can call it 9 new 1 equal to negative 3 new 2. All right. Now let's try to figure out what's going to happen. If new 1 equal to 1, what happened to new 2? If new 1 equal to 1, that part becomes 9. And how do I get 9 here? New 2 should be equal to what for for this to be equal to 9? Because if new 1 is equal to 1, this should be equal to 9. And how shall this be equal to 9? It shall be equal to 9 only if you multiply by negative 3. All right. So this is why you got a eigenvector of negative 1 and 3, as you saw here. Now, as I repeat to you, you could have replaced new 1 by 2. And then, of course, if you have replaced new 1 by 2, you will have 18 here. And then this one would have been 6. All right. Negative 6, excuse me. So here we go. That's how you get the eigenvector for the second value. So we've been able to get two different eigenvectors, an eigenvector for a first eigenvalue and another eigenvector for the second eigenvalue. If you had a 3 by 3 matrix, then you would have had to go more than that and find another eigenvector again. So having said so, we can try to understand how all this applies to the concept of principal component analysis now. But you will have an activity that you can do on your own, and we can discuss it later on, which is this activity. You are asked to find the eigenvalues and associated eigenvectors of the matrix. You can do that, and we'll discuss that later on. Okay? So how does all this concept of eigenvectors come in the concept of principal component analysis? So to understand that, we will see how eigenvectors is applied in the context of principal component analysis. Let's suppose normally what is going to happen is that you will have a data, all right? You will have a data set with several different variables, as I explained to you earlier. You will have a data set with several possible variables. And then you are going to apply principal component analysis on this data set in such a way that all these different variables will be transformed into a new set of uncorrelated variables. To be able to do this, you will be able to apply the principal component decomposition method. But before we get into the principal component decomposition, you need to understand that this method makes use of the concept of eigenvectors. So let me explain to you step by step how we are going to get to obtain what we call the principal components that I explained earlier. The first thing is that your data matrix should be a centered data matrix. That's very important. Now, you will see that I've written that you have a n by p centered data matrix. What does it mean? It means that you have p variables. P means the number of variables in your data set, age, gender, etc., etc. How many you've got? Let's suppose you've got 20. P is equal to 20. And how many policyholders you have? 1, 2, up to, let's suppose, n policyholders. Let's suppose 10,000 policyholders. I don't know. So this is what it is saying by n times p. So you have n rows in your data, and then you have p columns in your data, where n represents the number of records and p represents the number of variables. Then what we want to do, our idea is to find the eigenvector of what we call the variance covariance matrix of this data. Now, what is the variance covariance matrix of this data? Let me just give you a small example. If you have two variables x1 and x2 only, you know that you have a concept of covariance that comes in. You've already learned that uh, before in the context of correlation. You know that you can compute what we call the covariance. You can also compute the variance of x1. You can also compute the variance of x2. Now, if you think about it for a moment, just imagine you have all these different elements. The variance of x1 can be computed, the variance of x2 can be computed, and the covariance as well can be computed. That is the variation between the two together. You can also rewrite this in the form of a matrix where you have x1, x2, x1, x2, and then the first row and first column correspond to the variance because it's a covariance matrix. So the covariance of x1 is equal to the variance of x1, as we all know. Maybe I mentioned it earlier, I don't know, but if I didn't mention it, just let me just let you know that covariance of x1 is equal to the variance of x1. The covariance of y is equal to the variance of y, all right? The covariance of xy is a different thing. It's not equal to a variance, but the covariance of x or y, things like that, is equal to the variance. So here, in other words, you have basically the variance of x1 that is given. And for that column here, the second column and the second row, you will again have the covariance of x. You have the covariance of x2, which is the variance of x2. Then what you will note is you have a covariance of x1, x2 in the off diagonal covariance of x2 in the off diagonal covariance of x1, x2. They are going to be the same value here and the same value here. The covariance of x1 and x2 are in the off diagonal. So you've noted that we have something that we call a covariance matrix. All right, a covariance matrix is a matrix where you have all the variances and the covariances represented in it. So here I've taken the example of only two variables, but you can imagine having more than two variables, three variables, and so on. The more variables you have, the bigger the matrix will be. So what is an eigenvector then? The eigenvector is, what is the principal component do? The principal component decomposition P of your data X is basically defined as X times W. And what is W? W is the eigenvector of your covariance matrix. W is the eigenvector of your covariance matrix. So this is where you need to first of all find the covariance matrix. And when you found the covariance matrix, you can find the eigenvector of that covariance matrix. Now, what is a covariance matrix? Remember the concept of variance. The concept of variance is what? It is the sum of x minus x bar to the squared over n, right? The concept of covariance is what? You have in the numerator sum of x minus x bar into y minus y bar. So in whatever case, you know that you are taking a certain variable multiplying by itself somehow. So what we want to do, we are not going to work in the algebraic form like this, but we are going to work in matrix form, which means that if you want to find the variance covariance matrix, all right, for a set of data like this, what you need to do is to take the transpose of X, that is the transpose of your data matrix, the data matrix X here, you need to take the transpose of it, as I did here, multiplied by the data matrix as it is. So you will have a set of values everywhere here. You will need to take the transpose of that matrix multiplied by itself. That's the only way that you get squared values, or basically the covariance matrix, which we refer to them as a covariance matrix. So I repeat, you can basically take the transpose of that, you can take the transpose of that data multiplied by itself. This gives you what? It gives you a variance covariance matrix. Of course, you can't take itself multiplied by itself. You can't take a n by p multiplied by a n by p. That doesn't make sense. This is why you need to take the transpose of the matrix, which is a p by n now, multiplied by n by p, which yields a p by p matrix, which means that now if you have two variables, you will have a 2 by 2 matrix. If you have three variables, you will have a 3 by 3 matrix. And it goes on like that. So this is what you get, a covariance matrix. Having obtained this covariance matrix, the next step is to find the eigenvectors of that covariance matrix. Like, let's suppose you remember these example that we took here. Let's suppose this was a covariance matrix. Let's suppose this was our X transpose X, which we define as A. What we want to do is to find the eigenvector of that matrix. And the eigenvector, you have noted that there are two possible eigenvectors that we got, one for lambda equal to 8 and one for lambda equal to 2. For lambda equal to 8, we got, let me just move this on. For lambda equal to 8, we got 3, 1, and we got negative 1, sorry, we got 1, negative 3. So in other words, you got 3, 1, and you got 1, negative 3. You've got a matrix W which represent the eigenvectors, where the columns of this matrix W are the eigenvectors. You have a matrix W whose column represent the eigenvectors. And the eigenvectors of what? Of A, which is supposed to be our X transpose X. So this is what I'm saying here. We want, when we have obtained our variance covariance matrix, this is our, we call it, let's suppose we call it A. What we want to do now is to find the eigenvectors as we did. And when you got the eigenvectors for each eigenvalue, you will have a matrix of different columns which represent the eigenvectors. All right. But there is something I forgot to tell you before we move on, is that just remember that your data should be centered. That's very important. When you're talking about X1, X2, for example, if you're talking about age, salary, and so on, you can't take the data as they are. You have to center them. It's a very important step in your work because it ensures that the resulting components are only looking at the variance within the data set and not capturing the overall mean of a data set as an important variable. What do I mean by that? Let's suppose if you have x2, which is a variable on a scale of 10,000, and all the other variable x1, x3, etc. are on scale of 20, for example, or third on a scale of 10, right? On a scale of 10. You would note that this x2 will govern the analysis, will have an impact on the analysis because the scale is very different from the others. So to avoid having this issue, this is why you need to center the data because it will remove the variation, not remove the variation, but it will ensure that each variable has a say in the analysis. All right, because otherwise, what would happen is that x2 will have a greater impact in the analysis, which is not very good. All right. So, as I said, without this mean centering, the first principal component found by the PCA might correspond with the mean of the data instead of a direction of maximum variance. So a standardized data matrix is itself a centered data matrix. So if you want to center your data matrix, what you can do is to apply standardization, the concept of standardization, which is basically your x minus the mean divided by the standard deviation. You can apply the standardization of your data if you want to center your data, right? And you will know that if I'm talking about centering of the data, it is an assumption that your data is quantitative, obviously. If your data is not quantitative, you will have a problem applying the principal component analysis. That's another thing that you need to bear in mind. So, as I said, by doing this centering, you ensure that each variable contributes equally to the analysis. Otherwise, X2 will not be contributing equally with the others. All right. Basically, those variables with larger range will dominate over those with small ranges. Right. Like X2 is going to dominate the analysis, and it's not a very good idea. Now, having said so, this is why I said that you need to have your scaled covariance of a data first. Scaled covariance is very important because of this issue of one variable dominating the whole analysis. So I repeat, I've been talking a lot about different things here. So the first thing, you will have a data matrix n by p, which is supposed to be a centered data matrix. Normally, you won't have a centered data matrix. You will basically have to do some manipulation with the data. Depending on the package, some package you don't need to do any manipulation. They center the data automatically. But sometimes you will have package, means all packages, or sometimes you just have to do it yourself. Like you have to standardize and then you do the analysis. Otherwise, it might happen that the data don't need to be standardized because in the package it standardizes the data automatically. But irrespective of the package or not, you need to understand that the principle is that you apply principal component analysis on a centered data matrix. So you define a matrix W as the eigenvectors as that is the column of a matrix W to be the eigenvectors of the covariance matrix. Then what is the principal component decomposition? Principal component decomposition, we call it P, of your matrix X is basically X times W. So you just need to take x times your eigenvector and you obtain a transformed data. So you remember earlier I was saying that you have x1, x2, etc. And in the end you come up with z1, z2, etc. So what is happening here is that you add your x, your matrix X, which is our x1, x2, x3 up to xp, which has been transformed into a new set P, which correspond to our Z1, Z2, Z, and so on, by transformation, which is obtained by multiplying with the eigenvectors. By multiplying your matrix P with the eigenvectors, you obtain a transform data matrix that we call principal components. All right. So here we go. That's a little bit what's going to happen in the context of principal component analysis. And one of the things that you also need to understand is that when you have computed the different eigenvectors for these different uh, eigenvalues that you obtained from your covariance matrix, it is important that you understand that these eigenvalues themselves, they correspond to the variation in the data, right? They correspond to the variation. These eigenvalues, they are the one that gives you the variation in the data. It might say after having done your transformation, right? You might see that, for example, the first variable Z1 contribute to 80% of your variation in the data. And then you might have Z2, which contributes to 0.1%, and then the rest contribute to other percentage. So what is happening here is that when you are doing your eigenvector, when you're finding the eigenvectors, you want them to be ranked by the largest eigenvalue, which means the eigenvalue in a sense refer to the variation in the data. That's what it refers. All right. A and this is important as well because you don't want to make use of irrelevant variables. Like if you have 80% is already explained by Z1 and you have 10% explained by Z2 and the rest, like let's suppose Z3 is explaining not even 0.001%. Then you don't need to take the Z3. You just bypass it. You can use only these two variables, which reduces the dimension of your data. You remember earlier that principal component analysis is about dimension reduction, where you have different variable x1, x2 up to xp, and in the end they are summed up to a set of uncorrelated variables, but you won't be using all of them. You will use only the one that contributes to the highest variance. And this is what I'm saying here. We want the eigenvectors in W to be ranked by the largest eigenvalue. That is, the components which are the most explanatory power come first. All right. And the next step is what? To find out which of these different components have the least explanatory power. Because I just said to you that you have your matrix W, you have the eigenvectors and so on. You have obtained your P, which represent the principal components. I repeat, remember something is that originally you have x1. Let me just write it down there. x1, x2 up to xp. And then you have 1 up to n. These are your this represent your original data matrix X. All right. Now you can also find that of P. Now listen to this well. X is a n by P matrix. Now what is P? P, as we've seen earlier, is X times W. All right. And X is normally n times P. W is what? W is the matrix of eigenvectors. You remember that when you dealt with a 2 by 2 matrix, in the end, you've got two different eigenvectors like these. All right, two different eigenvectors. You could have rewritten all these two eigenvectors into only one matrix as you see here. And in other words, you would understand that if you have two variables, let's suppose x1, x2, you will always have a 2 by 2 matrix of eigenvector, just like originally your data was. So for us, if we had p variables in the data set, so we had 2 here, we have 2 by 2. If we had p variables, in other words, you will have a p by p eigenvector matrix. So if we have a p by p, you would see that it is a n by p matrix that you get. So if it is a n by p matrix that you get, you will see that now this same data is transposed into a new set of data z1, z2 up to zp again, starting from 1, 2 up to n, and this is just that now you are calling it p and it is a n by p matrix as well. So instead of having a value, let's suppose 10 here, now you will have a value of maybe 1.1 or 1.2, whatever, but it is standardized value obviously. That's a little bit the idea behind what we want to do to what we did by finding p. Now, but when we've done that, as I said, we want to know what we remember something is that originally I told you that principal component analysis is a dimension reduction method. What does it mean by dimension reduction method? If I originally had p variables and let's suppose p was, let's suppose 100 variable, it would be a bit crazy for me to again work with 100 variables like we have here. Here we still get 100 variables back. We don't want these 100 variables. We want to work with only a few set of uncorrelated variables. Maybe what is going to happen is that out of these 100, when you have transformed them into a new set of uncorrelated variables like these, here, what's going to happen is that you may finally come up with only 3 of them that you are going to use. Maybe Z1, Z3, and Z4, I don't know. Maybe only 3 of these uncorrelated variables are going to be used. Uncorrelated principal components are going to be used. How would I know which one needs to be used? How would I know which of these p uncorrelated set of new variables are explaining the maximum variance? How would I know that? I would know it by only doing something that I already did earlier. You see, if you want to find the variance if you want to find the variance covariance of this matrix X, what you did earlier was X transpose X. By doing X transpose X, you get a set of you get a covariance matrix. This I already explained to you earlier. But now, if you see the new set of data, all right? If you look at the new set of data, you can do the same thing. You can still apply P transpose P. That is, we call it P because here the matrix was called X. We call it X transpose X, but this matrix of Z values, we call it P transpose P. So we can again compute a variance covariance of these new sets of values. And I guess you would understand that all the diagonals of that matrix represent the variance of Z1, Z2, Z3, and so on, the variance of these different values of variation. But what about the off diagonal? That is, what about, for example, Z1, Z2? All right. So when you are going to do the covariance, when you are going to do P transpose P, remember that P transpose P, P is a N by P, transpose P is P by N, you get a P by P. All right. So what about the new? So you have the first variable 1, 2 up to P, and you have 1, 2 up to P. All the diagonals 1, 1, 2, 2, 3, 3 of the variance. But what about the off diagonal 1, 2, 1, 3, 1, 4, which represent the covariance? I think if you have understood well what I explained earlier here, what principal component is doing is that it is creating a set of uncorrelated components. Uncorrelated set of components. What does it mean by uncorrelated set of components? It means that if we talk about uncorrelated set of component, we come to the concept of covariance. Correlation is what? The covariance of x, y over the standard deviation of x times standard deviation of y. And if the correlation is zero uncorrelated, how would it be zero? Only when the covariance is zero. So remember that we have applied this transformation in such a way that this transformation has given to me a set of uncorrelated variables. If they are uncorrelated, you would have to understand that the off diagonal of that matrix P, which is a set of uncorrelated variables, are going to be zero. The covariance are going to be zero here. That makes sense because of what we just did. That's all what we wanted to do. We wanted to create a set of uncorrelated variables. So if they are uncorrelated, the off diagonals are supposed to be zero. The covariance matrix of P transpose P are supposed to be zero. But what about the variance then? The variance are not going to be zero, obviously. So we want to check the variance of the first variable, check the variance of the second variable. That's what I mean by the diagonal elements. All right. We want to check the variance of the third variable and so on. And then when we have checked the variance of all these different variables of the p variables, we are going to arrange them in order, in descending order, and see which one contribute more to the data, which one contribute more variation to the data. It may be, for example, a variable. Let's take only these two variables. Let's suppose you have 0.5% of variation is explained by the first, and you have 0.3 is explained by the second. Let's suppose this is the case. Then what is happening is that these two variables on their own explain 80% of variation in the data. So if they explain 80% of variation in the data, it means that they are good to summarize that data. They are good to reduce that data set into two new variables, Z1 and Z2, if they were to be the one with the highest variance, but it depends. It's not going to be like that necessarily. So that is the idea. You are applying dimension reduction in such a way by looking at what percentage of variation is explain the highest, what are the variables that explain the highest variation in the data. If two of these variables explain like 90% or 80% or 70% of variation in the data, then you can say, okay, we reduce the data to the two variables. If five variables summarize the data to, let's suppose, 70%, then the five variables are the variables that we are going to use to reduce the dimension of the data. That is the principal component analysis, what it is doing basically. So remember that we look at the first m diagonals to see which one we are going to retain for our analysis. Okay. Remember that we need to put them in descending order of variation first. All right. And normally the first principal component will explain most variation. Now, to explain the percentage of variation, you just need to take the first set of uncorrelated, the first the first percentages the first values that you got, okay, the scale covariance that you got in the diagonal, you divide by the total that you have. For example, you will have a total of 1. So you take 0.5 divided by 1, you know that there is 50% of variation explained by the first component. If you have 3 here, you have 0.3 divided by 1. If the total is 1, you take 0.3 divided by 1 and you get 30% of variation explained by the second component. Now, if you want to know these two components, how much they contribute together, So you just need to sum these two, 0.5 plus 0.3, divide by the total value for the diagonal elements, and then you multiply it by 100. So here it's going to be 80% if the total was equal to 1. All right. So this is what I say. It is the sum of the first m diagonal elements of S divided by the sum of all the diagonal elements. That is the proportion of variance. Having understood a little bit what principal component analysis is about, remember it's a dimension reduction method, and it is a transformation that you're applying to your data in such a way that you get a set of uncorrelated variables. Then you are going to choose only a few of these set of uncorrelated variables using what we are explaining here, right? Using what we are explaining here. And then when you've decided which one to use, then you will reduce your data set to that number, basically. So what is going to be the interpretation that you get behind the principal component analysis? You see, for example, as I said to you, let's suppose you have a different set of variables. These are the different variables in your data set, your x1, x2, x3, up to whatever. Then you have come up with a new set of uncorrelated variables z1, z2, z3. You see that there are the principal components, that is the value of p that you got in there. All right, p, you remember the p is equal to, it's equal to x times w. That's what you got as p. So this is what we are referring to here when you look at these principal component loadings. We call that the loadings, all right? Now, so yes, excuse me, normally here, these are the loadings, all right? These are the loadings, excuse me. These are the direction of the data. This is what is given here, the W, right? It's not P that is given here. So the loadings are what? You have the different set of new, the different eigenvectors, excuse me, the different eigenvectors of your data. If you had the P variables, you would have a matrix of the P by P, as I told you. So P by P means you have a variable name, and by P you have a different principal component that you can use as loading, the different eigenvector that you got for each of these P by P here. But the only thing is that, so I repeat, just if you didn't get me, the W is the eigenvectors of the variance covariance matrix. Now, normally it's going to be a P by P matrix. So as you are noting here, you have P variables, but you would also note that there is no P variables on in the columns. There are only three. So three means what? It means that you have selected only three principal components in your analysis. In other words, you are looking only at three eigenvectors out of the data, right? You're not looking at the whole eigenvector matrix. You're looking at only a subset of the eigenvector matrix. And this subset of the W that you are seeing here is what we refer to as the factor loadings or the principal component loadings. And the principal component loadings are very useful sometimes because it gives us some idea of what is going on in the data. It explains to us what does, when we have said that we want to summarize data to Z1, Z2. This is Z1, this is Z2, and this is Z3. We want to summarize the data to Z1, Z2, Z3. You would note that these Z1 sometimes they represent something, because what does it mean? If you add x1, x2 up to xp variable, you have reduced them to a few set of variables which are uncorrelated. It means that all the variables which were originally correlated among them, let's suppose that x1, x3, x10, and let's suppose x11 were originally strongly correlated. What would have happened is that when you are applying the principal component, these sets of variables will come up to be the new set of variable Z1. If you add a new set which are correlated x2, x4, x5, x7, then these were correlated together. They would create a new set of uncorrelated variable, let's suppose Z2, as you would note through the procedure that I explained earlier. So in other words, these Z1 that you are getting, they might mean something. They might have an explanation. They might represent something. For example, when you have applied this transformation of P is equal to X times W, it means that the new set of variables P that you got might be explaining something. All right, it might be explaining something. For example, here, according to this example, you will see that the highest magnitudes are here for Z1 for these different variables, which are chemical components. All right, you will see that these chemical uh, components, chemical components, and you will see that you will have Z1, Z2, Z3, and just take a look at what's going on. You have a look at the magnitude. You don't need to worry about the sign. The sign does not mean much in the with regards to the analysis, all right? Because it depends a little bit on the software that you're applying. So the sign, don't worry about it. But look at the magnitude of each of these variables. For calcium, you have 0.333, which doesn't mean much. It's just a transformation. But look at the sign. You will see that these four variables have high magnitude on the first principal component, that is the first transformed variable. And you will see that these three have a high uh, magnitude on the second one. And you will see that these one have a high magnitude on the third one. That could mean something, right? It means that when you see something like that, it could mean something. It could mean that the first principal component is explaining something particular, and it's explaining something related to calcium, silicium, sorry, not silicium. It is something related to calcium, silicon, iron, and aluminium. All right, here we go. So, in other words, what could it mean? It has a strong positive loading. What could that mean basically? It could mean something. If you were in the chemistry, if you were somebody who is in the field of chemistry, maybe you would understand this better, and this would mean that you are dealing with Z1, which represent pure limestone. All right, which represent pure limestone. Now, you may not be a person who knows a lot about chemistry. Even myself, I don't know much about chemistry, but I'm just trying to show you something, that these variables could represent something. These magnitude, when they are loaded on a variable, if you just look at the variable, all right, which have high loadings, we call that loadings, and the variables calcium, the variable silicon, iron, and aluminium have high loadings on PC1, that is on the first principal component. These other variables here have high loading on the second component, and the other variables here, magnesium, etc., have high loadings on the third component. In other words, if you are in the chemistry world, you will understand this better. Maybe they represent something, all right? Like in this case, the first principal components seem to represent something that we call pure limestone, because pure limestone contain these different elements. All right. So that's a little bit about the idea behind principal components. Remember what we just did is that in the end we have transformed a set of variables into a new set of uncorrelated variables, and through that we've been able to retain only a few of these several possible number of uncorrelated variables. Remember that you have p uncorrelated variables, but you have been retaining only a few, maybe three, maybe two, maybe five, I don't know, but which explain the maximum variance. All right. This is all about principal component analysis. We are going to apply all the different principles that we learned that is the principal component analysis on a data set which is available on Google Classroom, and this data set is called equity data set. We'll get into that later on, but before we move on to do an activity related to this data set, I just want to take a small, very, very small data set, a fictitious one, and work through this to illustrate all these different concepts that you learned with me. For example, when it comes to S is equal to P transpose P, and all these different elements like the eigenvector of the variance covariance matrix. We will also try to find the covariance matrix and so on. We'll take a very simple data set and work this out. So let's do that in R. We will also get to understand what is the concept of covariance here as well. Okay, so let's take a small data set where you have two columns in the data, 2, 1, 4, and 5, just fictitious one here. And you have Y where there are two columns, 4, 3, 4, 3, 1, and 5. Now, when you've got something like that, these are like the first column of the data, and this is like the second column of the data. I just gave it a name X and Y. I could have called them differently, X1, X2, whatever it is. But you should remember that when you are working with a data set, the data set is meant to be demeaned. That is, it has to be centered, as I said to you earlier. So one of the steps to work on any data set, if it is not centered, we will center it. But you have to understand something. What I'm showing you here is I'm showing you the different steps starting from the beginning to the end on how to get to apply the principal component analysis on this data to get the loadings and everything. But you also need to understand that instead of going through all the different steps that I'm going to show you right now, you can use a simple package, a simple function in R that enables you to do this. Whatever I'm going to do, you can use a simple function in R that helps you to get all these different information that I get through these different steps that I'm going to show you. But I prefer just to show you all the different steps so that you understand a little bit better the concept of principal component analysis, and you are going to refer to what I explained to you some minutes ago. Okay, the first thing is I'm going to demean the data. Let's call it the centered data, X centered. And if you want to find the centered data, you need to subtract the mean of X as the first step. And you're going to do the same thing for Y. We call it YC, we subtract the mean of Y. Now just note something. You have X, you have Y, which is like that. You have X, which has been demeaned or centered rather, if you want this term. Right? This is a data that has been centered where you took 2 minus the mean of X and you took 1 minus the mean of X and you got these different numbers, -1, -2, etc., etc. So remember the principle that before you apply the PCA, you need to ensure that your data has been demeaned. I'll just make a reference to what I'm referring to here. Just hold on a moment. Let me just show you that. Here we go. We said that we have N by P centered data matrix. That's the first step. We need to ensure that our data has been centered. Okay, and this is what I just did here. And then we are going to define a matrix W, which is going to be a P by P matrix whose column are the eigenvectors of the variance covariance matrix. So I think you would understand that to be able to get the eigenvector, we need to know what the variance covariance matrix is about first. But for the time being, we are not going to work in terms of matrix form. We're going to work it out as usual. Like I'm going to compute the variance on its own, and I'm going to compute the covariance using a simple function in R that allows us to do so. So let's try to find the variance of xc. We call it the VARXC. So the variance, as you know, is the sum of x minus x. So let me just write this down for you to understand. The variance of any data is the sum of x minus x bar to the squared over n. That's what we know. We also have a sample variance option, but for the time being, let's consider the variance from the descriptive aspect, like here, but by n. Now, listen to this. If you have demeaned your data, if you have centered your data, you should understand that the mean, the new data that you will get will be having a mean of 0. If you have centered your data, all the data, the new mean that you have for the new data will be equal to 0. Let me just show you this, for example. You have mean of x, you will see that it is equal to 3. Mean of y is equal to 3.25. What about the mean of xc? Logically, if you have already demeaned or centered the data, you will see that the mean of xc should be equal to 0, and the mean of yc logically should be equal to 0. So in the end, if you figure it out for a moment, what's going to happen? What's going to happen is that you have a new formula for the variance, which is a new formula for variance, which is now the new formula for the variance is the sum of x squared. Normally, it's not x, it's going to be something else, xc for us. Sum of x squared divided by n. Why? Because the mean is 0 for the new set of data. If it has been demeaned, it's going to be equal to 0. So in the end, it's just the sum of x squared over n. There is no need for us to write down sum of x minus x bar to the squared for this new data, for the new centered data, because if it's already centered, whether you subtract the mean or not, that doesn't make any difference at all. So this is why you will note that uh, I can compute the variance in a similar fashion here by taking the VAR VARXC, we call it variance of a centered data, is equal to the sum of the centered data to the squared, sum of x squared. But remember, it's not x here, it's the centered data that is squared. Divide by 4. This is the variance for the centered data. And we can do the same thing, of course, for the variance of y. For the variance of y. This is done. And for the context of covariance, I believe that you remember what covariance is about. All right. The formula for covariance based on what I explained to you earlier. All right. Let me just show you that. The formula for covariance is what? Sum of x minus x bar to the squared into y minus y bar to the squared over n. That is what we know about covariance, which you learned already in the, sorry, excuse me, not s squared. You have sum of x minus x bar into y minus y bar, not x squared, excuse me. So sum of x minus x bar into y minus y bar, this is what we know from the formula of covariance that we learned last time in when you were doing correlation. But again, as you will realize, if we are working with a demean data, a demeaned means a centered data, you will understand that your mean x bar of the centered data would be equal to 0. So in the end, the formula for covariance turn out to be just the sum of xy over n if your data has been centered. You don't need to worry about subtracting the x bar or y bar or whatever. It's just the sum of x times y, right? So xy over n, the sum of xy over n. That's what it becomes in the end, the covariance. But I repeat, this formula that I wrote or the other formula like this applies only if your data has been centered. If the data is not centered, that would not make any sense here. All right, that's not a variance. So let's get back to our we can find the covariance of x c y c. Covariance of x c y c is the sum of x c times y c, the x times y that I just showed you, but not for y original y, but for the centered data, divided by 4. Here we go. We can just check the values if you want. Variance of x c, variance of y c, and the covariance of x c y c. You got all these different values. Now, this is a little bit what you have. But bear in mind, if you might ask yourself, but what about if I were to use the formula, the function of variance that is given? Yes, you can use the function of variance that is given to compute that instead of doing what I did here. You can use the function of variance to compute that. You will get the same solution, but you have to be careful about one thing is that the variance function that R gives you, instead of doing the sum, etc., you could use the variance function that R gives you. But be careful about one thing is that the variance that R gives you is a sample variance function. All right. If you want to have the same variance like here, you need to multiply by the factor of n minus 1 over n. All right. You need to multiply by the factor of n minus 1 over n if you want to get the same variance that we got. Because if I just do variance of xc, you will see what I will not get exactly 2.5. You see, I get something else. But if I do variance of xc multiplied by n minus 1, which is the sample size 4 minus 1, which is 3, divide by n, which is 4, you will see that now I get the same variance. So just bear in mind that the variance function that R gives you is not the population variance, but the sample variance. So this is why you have to do this small manipulation if you want to get the same variance that I'm explaining here to be consistent with what I'm showing. So that's a little bit what you have, but you can also rewrite this down in the form of a matrix, all right? You can rewrite all the work that you have done in the form of a matrix as well. And remember something is that this variance covariance matrix that you got, all right? The variance covariance matrix that you got here, the variance covariance matrix that you got, which is a 2.5. Let me just write this down for you. Just remember that 2.5, 2.1875, and 0.25. 2.5, 2.1875, 0.1875 and 0.25 will be a matrix like that. All right. This is what we call the XTX that you've got here. This is your XTX. And from that, you can compute your eigenvalues and eigenvector and everything if you want. Okay. So let me get back to R. We are going to see if we get the same elements that you got here, but now not through algebraic manipulation like this, but through matrix manipulation. All right. We're going to have a look at if we do the same thing in terms of matrix manipulation, where we have to do X transpose X and see if we get the covariance matrix with these different elements 2.1875, 2.5, and so on. So let's do that. Of course, here I'm going to use a data matrix X that we just said, which is supposed to be the centered data. Do not forget that we are working with the centered data. So I call it matrix, but with the information of the centered data, not the original X, but the XC and the YC. All right. But then if you want the XC and the YC, what is going to happen? It will give you this -1, -2, 1, and 2. And then it will go for 0.75, -0.25. But you need to state that you want a what? You are interested in a matrix where you want it to be in 4 rows and 2 columns. So 4 rows and 2 columns because you've got 4 rows in the letter n. The number n is 4 and p is 2 in our example. You have like 2 variables x and y, but you have 4 records, 1, 2, 3, and 4 records. So you need to state that you want the data to include xc, yc, but by making it become a 4 by 2 matrix. And this is what I do by typing 4 and 2. And you can check the data. It will be in the required format that we want. -1, -2, 1, and 2 would be like this, and the rest will be in the second column. So instead of working with the original data X, which is 2, 1, 4, 5, you are working with the centered data. So what we want to do now, according to the principle that we explained, we want the variance covariance matrix, but this is done algebraically here, but we are not going to do it algebraically here. We are going to do it through matrix manipulation, which states that our matrix should be a transpose of x times x that you learned earlier. So let's call it a name. Let's give it a name A. At the matrix, we call it a name A. This variance covariance matrix. We're going to give it a name A here. You need to apply the transpose of x multiplied by x. This is what we have learned earlier. The transpose of x multiplied by x. Do not forget that we are doing matrix manipulation. Please refer to the first few lectures where we discuss different, where we introduce R to U. All right. So we are doing matrix manipulation. You need to do use these two symbols to multiply two matrices. All right. So we are going to take the transpose of x times x and see what we get from that. Let's type A. So when you look at this result, you will say, hey, I didn't get the same thing. Now you have to be careful about one thing, is that when you are doing this manipulation of transpose x times x, you are not getting the variance as such, but you are getting the covariance matrix where the principle is that you're not dividing by 4. All right, this is the only difference. You're not dividing by the denominator of 4 here. You are just applying the sum of x squared divided to the squared, sum of x c to the squared, and sum of y c to the squared. That's all you are doing through this principle here. You are not dividing by 4. In fact, the divide by 4 is irrelevant. In fact, you don't need to worry about the dividing by 4. But just for your information, let me just do, for example, a divided by 4, and let's have a look at what you get. You will see that you get the same thing, all right? Where now you will get the same variance and the same covariance. So we will see that you have a 0.25 and the 2.815. What 8175 is the same thing, the variance for the second variable and the variance for the first variable, and the covariance are in the off diagonal as you see here, 0.25. But as you will note, we don't really need to worry about the divide by 4, okay, because the division doesn't bring anything to the analysis. All right, if division by a factor of 4 multiplication by a factor of a certain factor of a quarter doesn't bring any change to your analysis. All right, your analysis will stays the same in the end, whether you are multiplying by a certain uh, uh, factor or not. So, in other words, we have done this first step here, which is the transpose of x times x. What is this step about? Let me just remind you. This is the step that we are talking about. Excuse me. Here we go. This is the step that we are talking about. We have computed the transpose of x times x. What is the next step? The next step is to find the eigenvectors of that matrix, of that variance covariance matrix. Now, you don't need to go and do it like I did here. We have the software to do this for you. If you add a matrix A, which is like whatever matrix you've got, you don't need to go through all these different steps that I explained to you here and to compute it if you have the software to do it. All right, so we are going to make use of the software and ask it to find the eigenvalues of that matrix, and we're going to call it a name, and we're going to give it the name W. So let's try to do that for a moment. So we're going to find the eigenvector of this data. To do that, we're going to call it eigen of A. Now, you have to understand again that when you are doing the eigen of A, if you were to do, if you were to find, listen to me well, if you were to find the eigenvalues or eigenvector of this data, using these different principles that I explained to you here, you may be surprised that you may not get the same result exactly like R is giving you. But you should not worry about that, because you have to understand something is that the eigenvector that you are going to get through R, if you want to know if it is correct, if you do the same procedure with manually, if you do the same procedure here manually and you check with R and you see that you don't get the same answer, it is not a problem, because if you recall what I told you about eigenvectors, all right, if you recall what I told you about eigenvectors, you have 3 and 1. But another possible eigenvector could be 6 and 2. Another possible eigenvector could be 9 and 3. Any scale multiple of any scalar of 3 and of a factor 3, 1 works out. So if the result of R is also a multiple of the one that you got manually, it should be okay. There should be no problem. Just bear that in mind. If you were to do it manually and you were to let R do it for you, you might see some differences in the result. All right, but it doesn't mean that your result is wrong or the result of R is wrong. It's just that it's just different multiples that is being presented to you. So if you do E, you will see that you will get your eigenvalues and you get your eigenvectors. All right, so basically here what is happening is this is your matrix W. By the way, this is your matrix W that you saw in the slide, but let's try to find the eigenvalue. If you want to extract only the eigenvalues, by the way, you can just do E dollar eigen E dollar values, excuse me. All right, E dollar values gives you only the eigenvalues. E dollar vectors, E dollar vectors give you only the eigenvectors, all right, which is here vectors. But let's give it a name. We're going to call it W to be consistent with the explanation that I gave you earlier. So here we go. We've got our matrix W, which is the eigenvector of your variance covariance matrix. So you've got your matrix W, which is the eigenvector of your variance covariance matrix. So the next step is maybe to find the component scores. We call that the principal component scores, P. So we will apply the principal component decomposition P of your matrix X, which is obtained by X times W, and then you will see that these refer to the Z values that I've been explaining earlier. All right, so what are we going to do? We are going to multiply X, the original, the X, centered data multiplied by W. All right, we're going to do that here. Let's try this. So we're going to call it P to be consistent here. Matrix P is equal to the matrix X. Remember that X is not the original data with 2, 1, 4, no, but it is the mean data, the center data, negative 1, 2, 1, 2, etc. Just bear that in mind. So X multiply, you are manipulating matrices. This is why you see me writing this percentage sign here. That's the way I'll deal with multiplication of matrices. So what are we getting here? We call that the component scores. This represent the component scores that we are getting, right? We are getting the component scores here. The P that you got are the component scores. By the way, the W that you got here, you remember, let me just quickly show you the W here, the eigenvectors that you got are what? This is what you get from the eigenvector, the loadings. We call that the loadings, all right? We call that the component loadings. These component loadings represent our matrix W. This data set, when you have at the original data set and you applied principal component, what you are seeing here as result here is just your factor loadings or principal component loadings that we refer to as the component loadings that we refer to as the eigenvector of your variance covariance matrix. So this is just for you to find yourself. If you got lost in all these different explanations, you can still trace back what I'm doing. So just let me remind you, W represent your component loadings. W represent your component loadings. P represent your component score. So I repeat, W represent I'm just writing it down for you to remember. W represents your component loading, all right? And P represents your component scores. This is something that you need to bear in mind. So let's find the P and show you. Now remember, what is going to be P? Remember, originally your data is what? Your mean data is this. Your matrix is negative 1, 2, 1, 2, etc. But now, when you're going to find P, P will be a transformed data set. A data set which has been transformed in such a way that the new variables that you have, these are the two variables, X and Y, original, but the new variables that you have will be uncorrelated. So you can check for a moment what is our P, that is the component code. Let's try P and you will see that you get a 4 by 2 matrix just like this one, 4 by 2, but you won't have negative 1, negative 2, 1 and 2. You will have something else. This is what you get. How did you get that? By this is basically a transformation that you got by taking your data multiplied by the eigenvector of your variance covariance matrix. It's a transformed data that you are working with. You have to bear in mind that the negative values are just an artifact of your computation. You don't need to worry too much about the negative values, all right? They don't mean much here, except that you need to look at the magnitude, which means something, all right? But this is a fictitious data, so we won't try to interpret the magnitude, whether this one makes sense or whatever it is. It's just a fictitious data, and trying to understand what's going on there will not help much. The next step would be to know, let's suppose you add more variables. If originally you did not have only X and Y, let's suppose you had x1, x2, x3, up to x10. All right. Remember that if you had up to x10, you would have 10 different columns of data. So the P, you would have 10 different columns of P, of transformed uncorrelated components. But these 10 different values would not help much. This is why we need to know whether we need to retain only 2 out of a 10 or we need to retain only 3 out of a 10, etc. And to know that, this is what I explained in this slide. Let me show you that. This is what I explain here through the matrix S P transpose P, which is a diagonal matrix where you get the diagonal element of a scaled variance of each component of a transformed data. All right. So let me just do that now. Let's try to find the variance covariance of the new or data, the transformed data. Let's try to find the variance of the transformed data. We call it S, as you note. And this is what? It's P transpose P. Transpose of P multiplied by P. All right? Transpose of P multiplied by P. This is our new matrix. You will see, look at that now. You see, originally for your original matrix X, you see that there was a covariance of 1. If there is a covariance of 1 or whatever value this could have been, it means that there is a correlation for that. But now look at what's happening. Is that when you have transformed your data into a new set called P, that is the component scores, now you will see that there is no covariance between these two. And this is exactly what we wanted originally. We wanted to create a set of uncorrelated data. This is what we wanted to do originally. All right. So here we go. We got our variance covariance matrix of the principal components scores, and we saw that these are 0. So by default, they should be 0. All right. You cannot have something like 1 or 2. If you got something like 1 or 2, you know that you have done a mistake somewhere. And to know what proportion of variation that each of these variables are explaining, this is what you need to do is just bear in mind something. If you have more than one, you have 1, 2, 3, 4, etc. This would be helpful, but here it's not really relevant, but I'm just showing it to you nevertheless. So one of the things that you are interested is to find the total sum of variance for the whole data set, the total variation for the whole data set. The total variation, let's call it total. It's a matrix. S is a matrix of 2 by 2. So you just need to take the first component and the first row, first column, plus the second row, second column. Go. And then what you want to do is you would have done that for more variables. If there were 3, 4, 5 variables, you would have done that for all these different variables and computed the total in the diagonal. And then you will see what is the percentage that the first explained for the diagonal, what is the percentage that the second explained for the diagonal, and so on and so on and so on. So you will see from that, for example, let's suppose the first one. The first component on its own explain what percentage of variation. So S11, which is 10.55, divide by the total that we just computed, explain 56% of variation of the data. All right, it explains 56% of variation in the data. So then you will need to check the cumulative percentage. If the first one you do it for the second one, you add them, you will see if there were more. I mean, if there were 5 variables or more variables, you would have done it for the first, you would do it for the second, you would do it for the third, and so on. You would sum and see what are the percentage of variation that they are explained by all these different variables, and you would know how many factors to retain. If you get, for example, 80%, that should be fine. If let's suppose 80% is explained by the 2 variables, if there were more here, if there were more variables and 80% is explained by the first 2, it's enough. You don't need to go more than that. You just take the 2. It's a bit subjective, but this decision on how many factors to retain, I'll get into more details about it next year. All right, when we do the module of data mining for actual science. But for the time being, note that if if the first 2 or the first 3 explain a large amount of variation, you should be okay with it. All right, you should be okay. But for the time being, I leave it a little bit as a subjective approach. But later on, you will see that it's going to be there is some means of finding that, which I'm not going to get into now. So you see, you've got your principal component loadings, but all these have been through the old procedure that I've explained to you. But now what I want to do is to show you one thing, is that all the thing that I've done through all these different steps can be done in a matter of only a few lines of code. A few lines of code. So let's do the principal component. You have two different functions that you can use. PRComp is one, all right, which is also which you can use. In fact, the PRComp function, which you can apply to on a data set to apply PCA. But there is another function that also we can apply, which is the printcomp function, all right? So let me just this. Here we go. So we have also the printcomp function that you can use to apply PCA. Now listen to this. Both these functions generally will not give you exactly the same kind of answer, but it's the interpretation that matters, all right? Because they use different types of computation for each one of them. But it's the interpretation that matters in the end, okay? When I say not the same kind of solution, it's mean, for example, if you are getting a negative values for this loading and these are positive on the other function, you might have a negative here and a positive here. It depends, right? But in the end, it's going to be the same interpretation that you are going to get from both functions that you are using. Now, each of them has their own advantages. I'll let you discover it by your own. And I'm going to apply only the print comp function for the time being here. All right. And let's have a look at, you will get different information. You have a standard deviation of the different components, which represent basically the standard deviation of these different components here. You can take the standard deviation of these values, you get 1.62. The standard deviation of these different values, you get 1.43. Normally, that's what it refers to, the standard deviation of these different principal components. Now, you can also get a summary of these different values. And you can have a look at what you get here, the summary. Which are provided. All right. We can also do something else. We can just type another function. Let me just try this for a moment. We can also change this number of decimal places. And there we go. You get an additional information by typing loadings equal to true. By typing loadings equal to true, you get an additional information with regards to the loadings of these different components. All right. We can just verify if we got something similar to this earlier. You will see that these different component loadings 0.875, 0.48. Here we go, the W, the component loadings, as I told you, the component loadings, the W. So it's the same thing, right, that we got here. Same thing, but the only difference is in the negative values, which are not the same. As I told you, you should not worry about that earlier. I already mentioned this to you. Not worry about the sign of these loadings, all right? They do not mean much in this context. What matters most is the magnitude of these loading. This is what you need to look at normally when it comes to interpretation of these different factor loadings, as you saw in your slide here. All right, we do not worry too much about these negative values, but it's mainly the magnitude that matters most. All right, so that's one thing that we need to know. And you can also get these scores, the factor scores. You can do str of r to see what are the different possible components that you get from these are. You can get the loadings as you see. You can get different information. You can also get the scores as well. So we can type R dollar scores and have a look at the different scores that you got here. And again, as I mentioned to you, you might have different um, different negative values or positive values that might change, right? Obviously, then the loading will change accordingly. So you will see that these different components 0.511, 1.87 are being given here. 0.511, 1.87. I repeat, do not worry about the negative values, all right? They are just an artifact of the computation. And you will see here that we got all this in just a matter of a few line of codes. Our print comp, and then you did a summary, you get some information that are available, 0.656. You know what is this 0.56? It represents the proportion of variation that is explained by the first component, and this is what we did here. You see 0.56, we did that. And then if you were to do for the second as well, you will know that the second is explaining 43% of variation, and the total explain 100% of variation, obviously. So that's a little bit with regards to understanding the concept of principal component analysis. All right, you've understood a little bit out what principal component analysis is. Now, the next step, obviously, is to apply it on the equity data that you've got earlier, right? To apply it on the equity data that I mentioned to you here. Oops. Here we go. This is the one that we want to do. We want to apply it on that data as well. Now, I'm not going to go through all the different steps from beginning to the end. All right, we can just go through a few steps and try to apply this on that data. The data that you get here is what you have on Google Classroom. You have the returns on the different market equities, all right? Returns on different market equities, and you might want to apply the principal component analysis to transform this whole data into a set of uncorrelated data and also see whether there is a kind of correlation between some of these markets. If there is some correlation between some of these markets, you may reduce that data set to only a fewer set of uncorrelated variables, all right? So that's basically the idea behind doing that. So we are going to apply that in our uh, as we as usual. So the first thing is you are going to set your working directory. I already have it ready. I'm going to set my working directory as usual. I'm going to read the data. The data is named equity.csv, and you have a header there. And normally, before applying the principal component analysis, it's always good to see if your data is linear or not, if the relationship between these different variables are linear or not. Because without this concept, without this linearity, you might understand that your data might require some transformation. Because generally, you apply a principal component analysis where your data is assumed to be linear, because correlation is an application when you do for data that are linear. Correlation is something that you apply for linear data. So if you want to apply principal component analysis, you also need to check if your data is linear. So we're going to do 1, 2, 3, and 4. We're going to plot all of them at one go and see what are the scatter plots. So more or less, it's kind of, you see, for example, market 4 and 3, there is kind of linearity. Market 2 and 4, you have a scatter plot matrix, we call that. It's a scatter plot matrix where you have market 1 and market 2. Market 2 for this plot here. Market 2 is in the denominator, market 1 is in the numerator. All right, so you see that there is a kind of linear relationship, although the relationship does not seem to be strong for market 3 and market 4, for example. There seems to be not much relationship between these two, but still there's a kind of linear relationship going on. So it seems fine. I can apply the principal component analysis. So otherwise, I would have had to do some transformation to the data by log application and so on. Now, uh, normally, you will note that if you were to go through the same procedure that I've been explaining earlier by computing the variance covariance matrix and everything, first of all, you need to center the data. Don't forget that. If you center the data, you go through all these steps, all right, you will see that you will get the same solution that I'm going to get by doing the same thing by using the printcomp function. All right. So uh, normally, if you have a data set like what you've got here, data, if you got this data set like that, you don't need to uh, normally go through all these different steps. What I did above was just to explain all these different concepts of principal component analysis to you. But if you have to do certain analysis, there is no need for you to go through all these different concepts, except if I ask you to do so. But if I don't ask you to do so, there is no need for you to do so. You just need to apply the principal component analysis function directly, the print comp function that I've been using here directly on the data directly. There is no need for us to go through all these different steps, as I said. You can call it a result. I don't know what you want to call it. Just call it result. And then you say print comp of data. All right. Now, note something. There is no need for me to do a centering of the data and then apply the print comp. The print comp automatically will center the data. You don't need to do it. So you see the advantage of using this function print comp. But bear in mind something. If you were to do it manually, like through these different steps here, then of course you would have had to center the data first. But if you are using the print comp function, by default, it will take the data and do the centering on its own. By the way, there is something else that you can understand is that you might also need to scale your data at times. All right, scaling the data is also very important. Scaling the data means you apply standardization to the data. Scaling the data is very important, especially it is standardizing the data. It's very important. Why am I saying so? Because especially when your data set are on different scales. For the case of equity that you just saw, they are on relatively similar scale. But for other data sets where the scales are very different, it's always very, very important that you scale your data first. You scale your data, and when you have scaled your data, let's call it S or whatever it is, you call it S or you call it whatever, you apply your principal component analysis on the scaled data. It's very important. Scaling means you are standardizing the data. And when you standardize the data, not only are you centering the data, but you are removing any variation effect with regards to the different variables. Like if one variable will not, it's like one variable will not contribute. Like if one variable is on a high scale, if you have standardized the data, that particular variable will not make will not affect your result. All right, will not affect your result. So you want all the variables to contribute equally to the analysis. So this is why the scaling is important. Not only are you going to center, but the scaling of the data is also important in the context of principal component analysis. You have seen that I did not do any scaling so far because if you look at the original data, all right, the data are more or less on the same scale. But let's imagine the market was, let's imagine you have different variables here, all the data on the same scale like you are seeing, but only one of these variables are on scale of 1100. then what would have happened if you did not scale the data? That variable will govern the whole analysis. All right, will have an impact on the whole analysis, and your analysis will be flawed because of only this variable. So this is why scaling is important. But me, I'm not applying scaling here, but repeat, all the procedure that I'm doing, you would have applied it on the scale data. All right, if there are data on different, if the variables are on different scale. So we are going to apply our principal component analysis on the data. Uh, I think I already did it here. No, I didn't do it. So let's call it our result or something like that. And then we are going to apply print of data. Now, when you've done that, there are different other things that I'm not going to go through here. I'll leave it for next year. There are something that we call the script plot and so on that enables you to decide on how many factors to retain. All right, but these are things that I'm not going to discuss in too much detail this year. You can do the summary of the result and with the loadings equal to true to get an idea of what's going on. Otherwise, it won't give it to you. And also decrease the decimal place to 2 digits, basically. And here we go. We've got all the different loadings. Remember what this loading represent? It represents your matrix W. All right. It represents your matrix W. You see that there is a blank here. This blank means that the value is very small. It's close to 0. It's very small and has not been included in the analysis. It disappeared. So I repeat, one thing is that you need to bear in mind that all these different components, all right, the negative values do not mean much in the analysis. So do not worry too much about it, about the negative values. But nevertheless, you need to understand that positive loadings indicate that a variable. Normally, you have to understand that positive loadings indicate that a variable and a principal component are positively correlated, all right? Like if you got a positive loading, it means that the variable and the principal component, the variable here and the principal component here are positively correlated. But as I said to you, that will depend basically on what package you're using, all right? The package might be here, another package can be used as well, and the loadings will be different. So that might change depending on the package. Now, but what matters most is the size of the loading. This is what matters most. Large loadings indicate that a variable has a strong effect on the principal component. A large loading indicates, for example, this loading of 0.621. It is large and it indicates that it has a strong effect on the on the first principal component. All right. Uh, so that's partly what I wanted to say. There is one thing that you also need to know is that the sum of the loadings are the sum of squares of each loading of all the loadings for a particular component sum to 1. All right, something that you need to remember. The sum of all loadings for a particular component sums to 1. If you take 0.481 to the square plus 0.621 to the square plus 0.434 to the square plus 0.444441 to the square, you will get 1 normally. So generally, if a particular loading explained for more than 1/4, because here you have 4 variables, so more than 1/4 is higher than 1/4, it is considered to be large. Higher than 1/4 means 0.25. So if a particular loading is higher than 0.25, it is considered to be large. In this particular context, all the loadings are relatively large. All right. Uh, but that's just a general rule like that, okay? But you can just also analyze it in relation to what is happening for the other loadings as well. For example, here you see that this is high loading on component 2. This one has a high loading on component 1, right? You will see that this one has a high loading on component 3. And sometimes you will see that these two have high loadings on component 4. So it's a little bit a matter of interpretation. So that's a little bit about principal component analysis. You have understood. Now, the last thing that before I move on, these loadings means what? It means that your different principal components can be explained by an equation, as you will see I've written there. All right. So the first component Z1 is equal to the Z1 is equal to 0.481 times market 1, the variable 1, plus 0.621 times the second variable, plus 0.431 times the third variable, and so on. So this is what you got here, 0.481, 0.621. So the component 1 is equal to this times the variable 1 plus this times the variable 2 plus this times variable 3, and so on. This is what we got here. So basically, when you look at this equation, it is our transformation that originally we have been talking about. You remember, you are applying a transformation on your data, your P, the Z values, the Z1, the Z2 that I've been explaining in the lecture, Z1 and Z2. So the Z1 is equal to 0.481 x1 plus 0.621 x2, and so on. So you are applying this transformation on your data to get your scores. You remember, the scores are dollar scores to get your different scores for your data. Sorry, result scores. Here we go. You got the different here we have here these. By applying this formula that I've just shown you here, the data can be transformed. The data which was originally, let me just show you that data which was originally here, of course, centered one, not this one like this, but the centered data, uh, not this as such, but the centered data has been transformed using the formula that I'm showing you through this loading here, the formula here, through this loading, and you get this equation, these values. So how did you get these values? These values have been obtained just by taking this equation, applying this equation. So that's a little bit all about how do we say it, about principal component analysis. Just bear in mind about something. It's very important that you also interpret the percentage of variation in the data. For example, here already 80% of variation is explained by the first component. If 80% is explained by the first component, only one component is sufficient to explain this whole data set. And in fact, you already saw it here because as I just said, each of these variables contribute to at least to more than 25% of variation for on the first component. So if all of them are explaining, so all can be explained by only one component, all of the variables can be explained by only one component. It basically means that all of these variables are correlated together. Maybe these markets are relatively similar in a way or the other. If we had more information, maybe we would have noted that these different markets are similar markets. That's why you are having all of them loaded only one component. Maybe if you had other markets, market 5, 6, 7, and you did not get all the loadings on only first component, it would probably mean that these four markets would be similar in a way, and the other three markets would be similar in a different way on a different components. But here, all of them are loaded mainly on the first component because they are relatively high values on the first component. Then there is no need for us to worry about component 2, component 3, component 4. These become irrelevant. Though I gave you the formula for the second one, maybe the second one would not be that much. So I'm showing you the first two components here, but maybe the second component would not be of much relevance here. Only the first component would have been sufficient. So you have finally come up to a reduction of your data to only one component. You had four variables originally, as you saw here, four variables which has been summed up to only one component, which are uncorrelated with the other components. So that's all for principal component analysis. We will get into more details about these next year in the module data mining for actual science.